right, we're into section 4. Just got 2 more sections to go, so this one and one more. But the learning goals that we're going to attack here are going to be: I can interpret energy changes and determine whether the reaction is endothermic or exothermic, and I can explain energy flow between systems and surroundings, and how this actually relates to the law of conservation of energy. Now, beginning of the year, we talked about law of conservation of mass. This is going to be a similar concept, looking at the total energy and in a system and where it goes and how that actually works out. Now, as said before, this is going to actually start us into the information for chapter 6. So, what is energy in all? Energy is the capacity to do work. In physics, we look at the 2 main types, and you've heard these probably a good portion of your life. We look at kinetic energy, which is energy of motion, and potential energy, which is based on the position due to gravity. In chemistry, we actually focus on heat energy gained or lost during chemical reactions. So we'll look at the particles, kinetic, as well as potential energy in order to understand a little bit of what's going on. Now, the SI unit we use for energy is going to be the joule with a capital J. Most times you'll actually see kilojoules, so you just know 1,000 joules. But 1 joule is equal to 1 kilogram times a mass squared divided by second squared. We also sometimes use the calorie, which is the amount of energy that's needed to braise 1 gram of water 1 degree Celsius. But the conversion is also there, that 1 calorie equals 4.184 joules exactly. Now, this calorie is different from what we deal with when you look at the back of your food or your drink and you see nutritional calorie. This is actually with a capital C versus a lowercase c, and it's actually 1,000 regular calories, which is 1 kilocalorie. Again, things that you'll hear throughout the rest of the time, but just keep in mind. Now, it does actually play a role, whether it's capital C or lowercase c, and we'll see this a little bit later on as well, where capital C will mean one thing versus lowercase c will mean something completely different. So be mindful of that as you use your calculations. Now, system and surroundings. When we do any type of reaction, we have to define 2 things. What is a part of the system, which is whatever reaction we're actually focused on, and what are the surroundings, which is everything else other than what we're looking at. So the example given to you here, if we're interested in the reaction between hydrogen and oxygen in the cylinder, then the hydrogen, oxygen, and cylinder are in the cylinder, are actually the system. Everything else, including the cylinder that it's in, are the surroundings. So we'll look at the energy transfer between those 2 things. This is going to play a little bit of a role in how we see what happens with our overall reactions. Now, there are 2 ways to transfer energy in and out of a system. We have work, which is applying force to something like a piston in a car. Or we have heat, which is, we usually see the energy transfer from hotter objects to colder. A way that you can test this is if you're in somewhere, you see something nearby that's metal or something that's usually cold as we would look at it, put your hand on it, rest it there for a good minute. Then take your hand away, then touch it with the other hand. You'll notice that it's warmer. What happened? It actually pulled the energy from your hand into the object, and then your other hand now actually feels that. So we can then define energy as the capacity to do work or the transfer of heat. We actually worry about the transfer of heat. Now, first law of thermodynamics. This was our good friend Newton, what he came up with. And it's basically the idea that energy cannot be created or destroyed, or law of conservation of energy, meaning that the total amount of energy in the system and surroundings is constant. For the energy lost, it's going somewhere, therefore it still has a net charge or net relationship of 0. Now, internal energy is going to be what we look at in terms of energy of the system. You can't measure absolute energy because of the fact that we're actually going to lose some in the process, or absolute internal energy, because of the fact that we lose some. So we have this relationship that we call delta E. Whenever you see delta, again, means change. The change in energy is going to be the energy, final energy minus the initial energy that we started with. You'll see some formulas like this very often throughout this unit. So just make sure you're keeping track of which one is there. This energy, again, is internal energy. Make sure you have that noted down. Now, when a system undergoes a physical or chemical change, The change in internal energy can be given as the heat added or absorbed by the system, plus the work being done on or by the system. So we end up with delta E, the change in internal energy, equals the heat plus the work done by that heat or done to that system. If we get these types of relationships, we can start to understand and interpret what's happening here. What do I mean? If Q happens to be greater than 0, then that means heat is transferred from the surroundings to the system. If it's the opposite way, it's less than 0, that means that heat is transferred from the system to the surroundings. So again, Q is greater than 0, the energy is transferred out of the system to the from the surroundings to the system, or if it is negative, heat goes out of the system. Now, similar thing for work. If work is positive, then work goes into the system or is being done on the system, whereas if it is negative, then work goes out and is being done by the system. Sorry. Now, depending on which one we deal with here, it'll determine whether something is called endothermic or exothermic. Now, when we break out the word endothermic, endo, we're going to think inside, or it's going to absorb energy. This is going to be what we deal with when Q is positive. So it means that the process, whatever the process may be, it's going to absorb heat from the reaction or from the surroundings. We're actually going to have some reactions that we talk about in kinetics that they cannot go forward until energy is actually added into the system. Sorry, that'll be equilibrium. So an ice pack, instant ice pack, endothermic reaction, it feels cold because it's pulling energy or heat out of the system, which might be your shoulder or your knee or whatever it is you injured. Now, an exothermic process is one that's actually going to put out energy into the surroundings, where Q is going to be negative. So if I was to burn a piece of paper, we'd be able to feel the heat coming off of the system. This would give us an exothermic reaction, meaning it's going out of the system, the burning paper, into the surroundings. Using the diagrams here, this also gives you an idea of how it's going to play out in terms of delta H. When delta H is greater than 0, that means we gained energy or we absorbed energy, which means it's endothermic. Whereas if we actually end up less than 0, it's going to be exothermic, which means we lost energy, we gave off energy. And we'll see this a little bit more in our energy diagrams. Now, to understand this more fully, we have to look at what we talk about is called a state function. Now, a state function only depends on the initial and final states of the system. What do I mean? Well, look at the diagram we have here at the bottom. We have 50 grams of water that starts off at a boiling 100 degrees Celsius. In the middle, we cool it down to 25 degrees Celsius. Still 50 grams of water, the temperature change is about the same. But if I took on the other side, sorry, realize you guys couldn't see that, water that was freezing, or blocks of ice cubes, and I heated them up to 25 degrees, that's all I'm concerned about is the final state. Given the example here, the altitude difference between Denver and Chicago doesn't depend on whether you fly or drive, it's only the elevation of the two cities above sea level. So it doesn't really matter the rest of the information. We're only worried about the final product. How do we get to that final product? Now, the state function does not depend on how the internal energy is actually used. So the example we have here, a battery and a flashlight can be discharged by producing heat and light. The same battery in a toy car produces heat and work. The change in internal energy for both is going to be the same. Does not matter what you were using it for, it's just the fact that it was used. Now, we'll move into the next part, and we sort of saved the math, I guess you will say, for the last section. So all the things we talked about before have been the theoretical part and understanding how we interpret the math that we're going to do next. Now we're going to put all that together. We're actually going to see the full picture of thermodynamics and thermochemistry and how it sort of relates to our overall reaction energy. Take a moment, look back at your notes, make sure you have everything together so that you'll be able to continue from here. Have a good evening, and I'll see you in class.